Good afternoon, everyone. Welcome to today's webinar. My name is Clinton Boyd. I am the Technical Director of the Michigan Green Chemistry Clearinghouse. Today, we are happy to broadcast the second webinar in our webinar series around toxicology training for green chemistry education. The first webinar was hosted on April 23rd of this year, and this is a follow-up to that webinar. This webinar series represents a project, a part of a project that has been was launched by the Michigan Green Chemistry Clearinghouse and the Grand Valley State University's Chemistry Department in an effort to bring about the inclusion of toxicology training in green chemistry curricula, which has been identified as a key learning objective widely recognized as being important for proficiency in green chemistry education. In June of this year, the green chemistry commitment was formally launched at the 17th Annual Green Chemistry Engineering Conference that was held in Maryland this year. Now, the Green Chemistry Commitment is a consortium program that has the mission of uniting the green chemistry community around a shared goal and common vision to integrate green chemistry into chemistry curricula at institutions of higher education. As a part of the Green Chemistry Commitment, once colleges, universities sign on to the Green Chemistry Commitment, they pledge to incorporate a number of different student learning objectives to improve green chemistry competencies. Those learning objectives include theory, toxicology, laboratory skills, and application. So this project was launched in an effort to address the learning objective around toxicology. So the primary objectives of this project are to initiate an open and transparent conversation with members of the education community in Michigan, including members of the Michigan Green Chemistry Education Network, other green chemistry educators, and any other parties that may be interested in the role of toxicology training in green chemistry education. So that's the first objective, to basically just initiate this conversation. The second objective is to generate open source learning materials to support toxicological implementation in chemistry curriculum, and thus the learning objective proposed by the Green Chemistry Commitment. And finally, this is very important. The first two objectives of initiating this conversation and generating open source learning materials. It's very important that we believe that is done in a neutral arena to showcase through these various learning modules and webinars developments in this very complex field, including perspectives around emerging science and new tools for predictive mechanistic toxicology. This is very important because as we talk about how toxicology should be incorporated into green chemistry education, we need to understand and appreciate the complexity of the science of toxicology, and we need to hear from a variety of different voices. So this webinar today is to announce this project and also to make people aware of it, and hopefully energize you to become involved in our project. So as I mentioned previously, this is the second webinar. The first webinar that was held in April, we had 3 speakers that gave us an introduction to toxicology and made some initial comments about how toxicology could be incorporated into green chemistry education. And we heard from Dr. Rick Rediske from Grand Valley State University, who gave us an overview of toxicology. We then heard the public health perspective from Dr. Carol Henry, who is with George Washington University and also a consultant for the Society for Automotive Engineers. And then finally, we heard an industry perspective from Dr. Pamela Spencer, who is with Dow Chemical. The PDF and the recording for the initial webinar can be found on the Michigan Green Chemistry Clearinghouse site. There is a page dedicated to this project around toxicology training. At the end of this webinar today, you will find there'll be a slide on the screen that will give you the web address where you can find that page. So today we're going to hear specifically again from Dr. Rick Rediske, who's going to take a bit of a deeper dive into the science of toxicology and how it relates to green chemistry and green chemistry education. And with that, Rick, I'll hand it over to you.
Okay, thank you very much, Clinton. And today I'm going to be presenting a kind of an expanded introduction to toxicology. Obviously, you can take a full multi-semester courses in toxicology, but I want to give you some of the basics of the science, and then talk about some of the really exciting opportunities that the bringing together toxicology and green chemistry can offer for a better environment and ultimately safer chemicals that we use every day. So next slide, please. Toxicology initially started out as the science of poisons, how to avoid poisoning, how to come up with effective doses of pharmaceutical compounds, things like that. But it's really expanded to something more, and toxicology now can be viewed as a science that deals with not only adverse effects of chemicals on living organisms, but also to be proactive and assess the probability of the effect on their occurrence. So it's got a little bit of a more proactive component now in the way toxicology is currently practiced. Next slide. So today I'm going to talk a little bit about the history of toxicology, and then get into the basics of dose response, which is one of the hallmarks or the central pillars of toxicology, and then get into types of toxicants. We have a whole variety of chemicals that can be hazardous. Some of the complexities of environmental toxicology. Again, toxicology kind of started just giving somebody a small dose, but when you get into environmental exposures, it gets very complicated. And then finally, some information on the role of toxicology in green chemistry. Next. And then the historical perspective, which is really interesting in terms of how toxicology becomes this more expanded science. Wanted to read a quote: "The appearance of a disease in human populations is influenced by the quality of the air, the food, the topography of the land, and general living habits." And that's a quote from a very famous person. And you can look at that and say, well, that might have been said in the 60s or 70s. But next, when you actually find out when this was said, it was said back in 400 BC by Hippocrates, the famous physician that was thinking about toxicology at the same time, the quality of air, food, and the environment. And I really encourage you to look at the Hippocrates Treatise on Air, Water, and Places. It's actually published, translated from ancient Greek, but it's published in its glory on that website. And you'll find that he's very much was interested in climate in addition to the quality of air. So this whole historical perspective, it's very in vogue now, but we've kind of forgotten that it was brought to our attention 400 years ago. Next slide. The founder of toxicology is Paracelsus, and that was done. He founded the discipline in the 1500s, and his classic statement was, "All substances are poisons. There is none that is not a poison. The right dose differentiates a poison from a remedy." And that's the classic dose-response idea that's fundamental of toxicology. So he came up with that observation back in the 1500s. Next slide. And then in 1815, the Spanish physician came up with or decided that toxicology should be a separate discipline, and he's considered the founder of the science of toxicology. And you can see that it came out of the medical profession. So these are three of the pillars. There's many more people that were involved, but these are the three people that I look up to as far as founders of toxicology. Next slide. So toxicology is a very diversified science, and I know I have a number of students listening. So you can study toxicology in many ways. You can obviously take a toxicology class as part of your training, but if you are motivated to study it further, we have mechanistic toxicology, and that's actually looking at how a chemical causes a problem in terms of absorption, distribution, excretion, the actual mechanics of the toxicological process. And then we have descriptive toxicology, looking at endpoints, doing different organism studies. And then we have clinical toxicology, looking at toxicity with respect to humans and populations. This is mostly drugs, but there's also some possibilities with environmental toxicants. Next slide. We have forensic toxicology, where you're looking at cases of poisoning, trying to find out why somebody died from a forensic or police standpoint. Then we have environmental toxicology, and that's looking at pollutants, how they affect not only humans but other organisms, ecosystems, and the biosphere. You get into the chemistry of toxic chemicals and also the ecological effects. And then finally, the regulatory side of toxicology. And we can have regulatory toxicologists in both the public and private sector. And these are the people that are trying to look at scientific data and come up with ways to protect humans and animals, humans and the environment from excessive risk of toxic chemicals. So there's a variety of options that you can take if you're interested in pursuing toxicology as a career. Next slide. So I mentioned dose and response, and these are the two hallmark parts of toxicology. The dose is the amount of chemical entering the body, and it's usually expressed as milligrams per kilogram body weight. If I was a physician providing an anesthetic to somebody, I would look at, the weight. A child would get much less anesthetic than a full-grown adult. So we usually express the dose of a chemical as milligrams per kilogram body weight. And then the dose is dependent, of course, on the concentration that you're administering, but it's also dependent on the property of a toxicant. If you have a toxicant that's metabolized very rapidly, you might have to give it a higher dose than if you have a toxicant that, or a chemical that is metabolized slowly and stored in the fat. It's got a much lower threshold. It's actually more toxic than something that's cleared very rapidly. The timing and frequency of the exposure, is it a one-time exposure? Are you exposed every day? Are you exposed at a particular time of the day? The length of the exposure, and finally the pathway. Is it, are you exposed in the food, in the air? So dose is not something that's very simple. It can be very complicated, especially with environmental toxicants, where you can have multiple types of exposure. Next slide. And then response, that also can be complicated, and that's the degree of deviation from some type of a normal state. So what is that normal state? It could be molecular, cellular, organ level, organism level, or even ecosystem level. So some type of a chemical causing a deviation at any one of those particular points. We can have local and systemic toxic responses. A local response might be skin irritation. Systemic is something in the lymph system or one of the organ systems in the body, something much greater than just a local impact. Some of the responses are reversible. You take the toxicant away, the irritation goes away. Some of them are irreversible. Some of them cause permanent damage. You can have a delayed or an immediate response. And then we get into the shapes of dose-response curves. We can have monotonic curves, which is a response that increases with dose. Cyanide's a good example. There's a threshold for cyanide, and then as you give somebody more cyanide, there's more and more of a toxic response. But then, nature, human systems are actually more complicated, and we can have responses that do not increase with dose. And those are chemicals like hormones, endocrine disruptors, micronutrients, and vitamins. So we have a whole host of ways organisms can respond and the way we can study them, their response in the laboratory. Next slide. In terms of the types of chemicals that are hazardous or toxic, we have toxins, which are biological compounds, things like ricin, botulism. snake venom. And a lot of people just use the term toxins to refer to toxic chemicals in general, but a toxin, to be correct, is a biological compound. Something that's man-made is not a toxin. It's a toxic chemical. Then we have carcinogens. These are materials that cause cancer, and they affect cells or tissue. Benzene and gasoline, vinyl chloride, benzopyrene, and smoke. These are examples of carcinogens. We have mutagens that cause hereditary genetic defects or increase the incidence of effect on a germ cell, the gonads primarily. And these can be agents like ionizing radiation or nitrosamines that are found in processed meats. We also have teratogens. These are chemicals that cause non-hereditary congenital malformations, and that's damage to the offspring. Measles, rubella is an example of a disease that causes that. I mean, there's chemicals like thalidomide, or pharmaceuticals like thalidomide, and then chemicals like PCBs and dioxins that influence the offspring. And then finally, we have endocrine disruptors, and these are materials that mimic or disrupt hormonal systems. And PBDE, the flame retardant, and BPA, one of the plastic materials, these are examples of chemicals that could be or are endocrine disruptors. Next slide. In terms of toxicity, we can look at various endpoints or various manifestations of the toxicity. And we can have a chronic toxicity, which is a sublethal concentration. We can have tests to measure chronic toxicity, and that's the effective dose that causes, ED50, that causes 50% of the population to be affected. And the effect is anything but death. And the ED50 is obtained by plotting the dose and the proportion of the population that responded to a dose. So the next slide will show some dose response curves. Next, please. Excuse me. We have also, in addition to chronic toxicity, we have acute toxicity. And those chemicals that are acutely toxic, that involves lethality, and the endpoint is death. And instead of the effective dose, we have the lethal dose, 50. And we obtain that by plotting dose response curves too. So next slide, please. There's my dose response curves. And this is an example of a monotonic dose response. And you can see that as I administer more of a toxicant, the response, the number of organisms responding, increases in a manner described in the graph. And if we look at the 50% level, we can see that the dose, the lethal dose of this particular chemical is 20 milligrams in terms of the dose response curve. So we run different exposures, we plot the curve, and then we extrapolate the 50% curve. That's kind of how we rank a lot of toxicants. Next slide. I also want to show some, draw some attention to different parts of the curve. And you can see the 50% level with the arrow, but you can also see two other levels. And the first one is the no observable effect level, or NOEL, and that's the concentration where you do not, the lowest concentration where you don't see an effect. You can see there's one point to the left of that, and then at this particular point is where the curve starts to increase. Also, the lowest observable effect level, or LOEL, that's the concentration that where you can actually see an effect. So there's two very important parts of the curve, and sometimes, well, very rarely do you actually hit those when you're doing your experiments. They're always extrapolated, but you can see a concentration where there's no effect, and you can see a concentration where there's a low effect, either by extrapolation or, you know, in rare cases by actually hitting them in your experiments. Next slide. And then we can kind of rank the potency. You know, how strong of a toxicant is it? How strong of a endocrine disruptor it is by plotting those dose-response curves. And you can see as you're moving further to the left, the threshold is lower, and as you move to the right, the amount of chemical to produce an effect increases. And if you plot that way, you can see the one on the left is more potent, and the one on the right is less potent in terms of the concentrations causing an effect. So that gives you, this is an example of anesthetics causing a neuromuscular block, and you can see that the chemical to the furthest to the left causes that effect at a much lower concentration than the one on furthest to the right. Next slide. So in terms of looking at some of the other chemicals, these are examples of traditional toxicants. We also have, as I mentioned, carcinogens, and these are chemicals that cause cancer. And it's theoretically possible that one molecule of a chemical may produce a mutation. That's a very theoretical type of observation because organisms do have a lot of repair functions. Our cells, our bodies have a lot of defenses, but there is a small amount of risk associated with one chemical or one molecule of a chemical. We look at cancer-causing chemicals by risk assessment because of that. In general, we'd like to have like a 1 in 1 million risk, and 1 in 1 million risk is considered to be acceptable for society. But unfortunately, we can only measure 1 in 100 risk with respect to laboratory animals. One incidence of cancer per 100 animals is about the lowest that we can measure in the laboratory. The other problem with these types of chemicals is we can't use high-dose experiments to extrapolate a lower dose. When you introduce high doses of a cancer-causing chemical, it often causes tissue injury, which will induce cancer, and we're looking at mutations at much smaller concentrations, so it's difficult to extrapolate our data from a high dose. So the way we assess what is a safe level of a carcinogen is pretty difficult to do. And then we have U-shaped dose-response curves, which are called hormetic or hormesis, and these are examples of some of these non-monotonic curves, and it's characterized by an initial dose causing a benefit and then increasing doses causing a toxic effect. And examples of this are nutrients, vitamins, ionizing radiation. Next slide. And you can see an example of a essential nutrient. Something like vitamin A would be an example where when you're given vitamin A, it has a beneficial effect on your body, and then you can take too much vitamin A and get toxic effects. So you see there's a benefit, and then as you increase the dose, there's really no benefit, and then after that it becomes toxic. And you can see a threshold toxicant to the right of that curve, and then a non-threshold toxicant, like I mentioned, the potential for carcinogenic chemicals on the other side. So this gives you an example of what these different curves would look like. Next slide. So endocrine disruptors are kind of a special case, and they have different dose-response curves. And just to introduce the concept, these are synthetic or naturally occurring chemicals that affect the endocrine or hormonal systems in animals. And they can do that by mimicking hormones, blocking hormones, directly stimulate or inhibit the endocrine system. So they have kind of a broad way they may interact with animal systems. Next slide. And the way these endocrine disruptors and hormones act is they bind to some type of a receptor molecule. So it's the classic lock and key idea of enzymes and receptors. They bind to some type of a receptor molecule, and they have these non-monotonic dose-response curves. They can stimulate at low doses, and then as you increase the concentration, there's really no change in the response because all of the receptor sites are saturated, and you can get very complex reactions with cross-reactivity. The endocrine disruptor can, somehow change the way it reacts in a small way or a large way. In the case of these chemicals, very low doses, femtograms, nanograms are significant. Hormones are very active at low concentrations. And again, we cannot estimate the toxicity of these chemicals with high-dose experiments either. So these are much more of a challenge to address with laboratory experiments. Next slide. And here's a kind of a basic diagram of how these endocrine disruptors work. You can see a hormone and receptor on the top left figure there, and you can see that the hormone binds with the receptor and produces a response inside the cell. You can see with the next example where we have something that kind of looks like the hormone but has a different molecular shape, and it reacts, in this case, with a receptor and causes an identical response because that little piece that fits into that receptor molecule is very similar. So even though the molecule might look different, it's got a little chunk of it, a little functional group of functional molecules that or atoms that will fit right into that receptor cell. So you can see that in that case it produces the same response, but it can also produce a different response. Next slide. And a good example is tamoxifen in cancer. That's a drug that was developed to treat breast cancer. And you can see from this example here that estrogen binds to a receptor, and that receptor binds to some coactivators, and that causes enhanced cell proliferation, and that can cause extra estrogen can actually promote breast cancer. Tamoxifen will react with the estrogen receptor, and you can see the shape is different, and because it's reacted with a different shape, it doesn't fit into the coactivator, and it tends to inhibit the growth of breast cancer cells. Next slide. And here's an example of two drawings. You can see estrogen, which is the pink molecule, and you can see tamoxifen, which is the red molecule. And it's got, tamoxifen is obviously a much larger, different stereochemical model, but the base of tamoxifen fits very nicely over the estrogen molecule. Next slide. Or next. And here's some three-dimensional renderings of how estrogen and tamoxifen might fit those receptors. And you can see estrogen forms a nice bridge across. Tamoxifen, which is in the center, does form that bridge, but you can see it's got that ring part sticking up, and that's just enough to cause it not to bind to the coactivators. Next slide. And then I mentioned about non-monotonic curves, and this is an example of how complicated the dose response of endocrine disruptors or hormonally active compounds can be. In the case of tamoxifen, if you start administering it, you can see that a very low dose will actually increase tumor growth. So you have to have a high enough dose. You can see there's, call it tamoxifen flare, where it actually promotes tumor growth. And then once you reach a certain level, it starts to dramatically decrease tumor growth. You can see then it flattens out. And finally, once you reach a high enough level, it actually causes acute toxicity. And you can see a no observable effect level. But this type of a dose-response curve is totally different than a standard toxicant, and you can see the difficulty of trying to assess this in the laboratory, on a large scale. Next slide. And then to complicate things even further, I mentioned the human body being so complex. On the left side, again, is the example of tamoxifen with binding with estrogen receptors and preventing the activation of cell proliferation for the tumor cells. Tamoxifen also can react with an estrogen receptor for uterine endometrial cells and cause cancer. It can cause endometrial cancer rather than uterine cancer rather than breast cancer. So, you know, one drug can have a very beneficial aspect, and it can also have a detrimental aspect. So when you're looking at how endocrine disrupting chemicals can affect the body, you really have to do a comprehensive study because you have so many endocrine systems and they're all sort of interrelated. So if it doesn't happen with one endocrine system, there's there could be a chance that it might interfere with something else. Next slide. And then we talked about populations, sensitive populations, and toxicity changes across the population. There's some sensitive subjects and some subjects that are less sensitive. And next, please. You can see with drugs of abuse, the fetus is very sensitive, much sensitive, more sensitive than adults. Next slide. Next two. And then on the far side of that, whoops, can you go back? On the far side of that, we have you know, people like Keith Richards and Ozzy Osbourne who seem to be able to withstand exposure a lot more. So within any population, you have very, very sensitive parts of the population, and these are the ones that we need to protect. Next slide. And then the example is ethanol, and that's something everybody's familiar with. Next slide. And, you know, people joke about ethanol all the time. This is a little cartoon that, you know, people always joke about ethanol killing brain cells, and in this cartoon, you know, he's going to go into politics after he drinks. So sometimes chemicals like ethanol we kind of joke about, but it's actually got a very serious side. Next slide. You can see from a toxicity standpoint or a potency standpoint, ethanol is you know, less toxic than table salt. Next slide. But in terms of toxicants, it's a group 1 human carcinogen. It's known to cause liver cancer, and it exhibits hormesis. Small amounts are beneficial. Next. It's a tetratogen, or a teratogen that causes fetal alcohol syndrome. Next. And the Institute of Medicine's report to Congress identified alcohol as by far the most serious neurobehavioral effect on the fetus, more serious than cocaine, heroin, or marijuana. So it really is nothing to joke about. It's a very serious toxicant with respect to the fetus. Next slide. And the reason why it's so potentially dangerous to the fetus is that it diffuses through the placenta, so it goes right in to the fetus. The concentration is the same as the mother's blood within a few minutes. And because we can metabolize it faster in our liver, the fetus can't. It's metabolizing that alcohol only 10% as fast, and they estimate 1 in 200 individuals have some effect from prenatal alcohol exposure. So it's a very serious toxicant. Next slide. And the reason why, and this you know, can be carried across to other types of toxicants, endocrine disruptors, is if you look at fetal development, you can see that during weeks 3, 4, 5, and 6, you can see the central nervous system being formed. Any exposure that you have during that particular time, you know, is much more serious than exposure later in life. And chemicals like lead that can also influence the central nervous system. You can see that even after the child is born, there might be some problems. The other systems, you can see that if you have an exposure to a chemical that influences eyes or teeth, or the ear, hearing, or the lungs, or the legs, anytime you have an exposure during those critical times, it can be much more serious than an exposure later on after these organ systems have been more fully developed. Next slide. So that brings me into environmental toxicology, and because of all the problems about, or all the complexities of environmental exposure, and not only that, but also with on the human side, I just have a little figure that shows all the different disciplines that have to be involved with environmental toxicology. And you can see it covers everything from molecular genetics to mathematical modeling to biometrics, risk assessment. Then you get into the exposure side, and it's not just, you know, inhaling or ingesting something. You have to look at the fate in soil, geology, landscape ecology from Hippocrates, and then evolutionary biology, population biology. So there's a lot of disciplines that come into environmental toxicology. Next slide. And this is a very good depiction of dose, how hard it is to come up with you know, an estimation of dose, because industries or chemicals can get into consumer products, they can get into the workplace, they can get into our air, soil, and water. They can be transmitted to humans from food, from consumer products, and then transmitted to the fetus at the bottom of that slide. So assessing dose is one of the very difficult problems of environmental toxicology, and yet it's, you know, so fundamental. We have to look at all the ways that a chemical can get into either a human or into a fetus. Next slide. So what's the role of toxicology in green chemistry? And we can kind of think about that figure that I just showed. If we can somehow link molecular structure to hazard and come up with chemicals that don't pose that hazard to human health and the environment, all of a sudden, you know, all those complexities are no longer relevant. So what we need to do is use toxicology and focus less on minimizing risk through reducing exposure. A lot of the science of like industrial hygiene and toxicology has been related to how can I minimize an exposure. But what we should be doing is focusing more on minimizing the hazard by designing chemicals that are safer, that don't have that inherent risk to endocrine disruption or the inherent risk to toxicity in the environment. And there's a standard equation of risk equals hazard times dose, and you can see that we can lower the risk by either changing the dose or working on the hazard side. So we can control that hazard part by manipulation of the molecular structure. Next slide. Or next. And you can see at the bottom there, it doesn't come through as well as I thought it would, but you can see that hazard identification in terms of risk assessment is actually the first step. So again, toxicology allows chemistry to focus on that hazard. We can identify what types of chemicals or what types of structures are hazardous, and then feed that into the whole dose-response curve. Next slide. There's two interesting approaches that we can do, and this is regulatory toxicology. We can take our knowledge from past toxicity testing. We can use computer models. There's QSAR, which is structural activity models, or QSTAR, which is the toxicity relationships, structure toxicity relationships. We can actually look at molecular structures like in pharmacology, but in toxicology, and come up with, you know, when we design new molecules, we can run them through these models. And then we can use other predictive methods to look at toxicology in terms of bioaccumulation, molecular structure, molecular size. And finally, we can come up with, by design, a better chemical by just things that we can do with computers and in your mind and on sheets of paper to come up with better molecular designs. Next slide, or next part. And then we can actually develop a tiered approach to assessing the hazards that are associated with chemicals. We can do these computational assessments, and if we have a chemical that comes out that it might have any of these kinds of properties, then we can do some very high throughput in vitro or in vivo screening tests. If it shows some possibilities there, then we can jump up to the next level in terms of cell activity. And then if the chemical is still showing that it might be hazardous, we would have to bring it through fish and invertebrate tests, and then finally mammalian tests. And as you jump into one of those steps, you can see that the cost associated with putting a chemical like that out to market in a consumer product would go up dramatically. So if you can go with Tier 1 and Tier 2 and design something that's safe, check it out with some high throughput tests, and then maybe some cell activity tests to confirm that, you're doing much better than trying to run it through all these different screening levels, have a chemical that's hazardous, and then try to minimize exposure. So again, the idea of being very proactive with toxicology, coming up with that safe design that doesn't have the ability to affect the endocrine system, is by far a more proactive role. Next slide. So just to show some examples, we talked about endocrine disruptors. You can see estrogen. It's got that terminal OH group in the benzene ring. And then you can see nodal phenol, which is in shampoos. And you can see from these other molecules, it doesn't really look like estrogen, but it has that one little functional group at the end there. And that's what causes the problem where these chemicals can react. So if you wanted to design something, you would design that functional group out of the particular chemical. Next slide. You can see in this example, again, estradiol, estrogen, bisphenol A. You can see that it's got some type of overlapping structure. You can see they both kind of look alike, but estrogen has that little flip on it. So there's a metabolite of BPA that does have that flip on it. So again, if you were designing a plastic chemical, why not come up with a design that doesn't match estradiol or have some of the similar properties or can be metabolized? That generally will be much more beneficial to business and to the environment than to try and limit exposure to a chemical that has some of those similarities. Next slide. So finally, to sum up everything, toxicology is a very complex science. It's based on this dose-response principle. And environmental exposures really add complexity to this concept of dose response. And things like the sensitive groups, you can see how a simple dose response gets very, very complicated. And we should be focusing more on minimizing hazard by designing safe chemicals rather than trying to do all the complex studies. Something that's hazardous, we should try to focus more, be more proactive with respect to designing out that hazard or designing safe chemicals. And if you marry or bring together toxicology and green chemistry, you can have a good way of providing a solution to these issues that we seem to be always reacting to, and we can be proactive. So that ends the webinar.
All right, thank you, Rick. I'm very impressed how you can summarize such a complex science in 45 minutes, and I think we can all appreciate that that complexity of toxicology is becoming more and more complex. And the more we learn about chemicals and the various ways in which they interact with living systems, but as I say, with every challenge there's an opportunity, and the opportunity here is that toxicology and green chemistry are working together, hopefully looking through that lens of hazard reduction. And like you say, the molecular structure of compounds, trying to understand inherent hazards and associated risks.
That's why we need more students involved too.
So while we're waiting for questions to come in, just to remind you, up on the screen now are some web addresses. Like I say, this webinar is part of a much larger project around trying to encourage toxicology training to become a standard part of chemistry education. And so the home of this project, you'll find it on that first web address. If you go to the Michigan Green Chemistry.org website and click on the Education tab and look under that menu, you'll find a page called Toxicology Training. And from that site, we'll start posting these webinars, the video recordings, the PDFs, resources, links. And as the project unfolds, and we start developing those open source materials, which will be housed in our virtual learning environment called Moodle, which is a separate platform run by the clearinghouse, but you'll be able to access all those resources, from this landing page, the toxicology training page. Also, if you're not, if you have a question that you'd like to ask later on, please feel free to to email that to Michigan Green Chemistry Clearinghouse at any time, and we'll get you an answer for you from our presenters, read today, and our previous presenters, and our future presenters. And that email address is very simple: migreenchemistry@gmail.com. If you forget the email, again, just very easy. If you click Contact Us on the Michigan Green Chemistry page, that email will come straight to us, and we'll make sure to get you an answer. All right, so we do have a question that's come in. So the question is, whose job is it now to ensure that our synthesized chemicals are not toxic? Government, industry, scientists?
All of the above. The burden should fall on the industry that's producing a chemical. However, the government obviously has to have a regulatory role over that, and scientists, have to be right in there in that process, applying the best science to make those determinations. So, it's really all three working together. And scientists can both be governmental and academic, but you have to have a combination of government, industry, and science all working together with that goal. And the goal of safer chemicals is good for sustainable business. So everything fits together.
Great, thank you. Following on from that, Jermaine, to your comment about the burden of proof should be on industry, the follow-up question is, what is being done to encourage those in industry to synthesize less harmful chemicals?
Well, like I said, many industries are very focused on building sustainable businesses. Some of the previous business models were not, we're trying to make maximum profit and, the heck with the future. But, companies have looked much more longer term now. We used to look at cradle to grave. Now we're looking at cradle to cradle with a lot of chemicals. So, the industry, I think industry is getting much better at looking more long-term and looking at the safer chemicals. And the reason why they can be more successful with that is just because science is coming a long way, and they're getting the science tools. So a pesticide that was designed 20 years ago, the process to design a pesticide now is totally different because they have better tools, and they industry does want to produce something that's safe and can be used a long time. It's very expensive for them to respond to lawsuits. It's very bad to have environmental damage, and it's much less costly in the long run to design a safe chemical from the start. So I think that's how I would answer that.
No, so Rick, if I may, I'll just add there, that is the promise of green chemistry. So I think it's important to recognize that green chemistry kind of focus on that hazard reduction part of the risk equation, but it does that primarily at the design phase. When we are designing those new chemicals or those new materials, and that's the intent. But one of the challenges that's been well recognized is that in order to design something better, you need the term I use, you need to design signal. What's the feedback that enables you to know whether or not you've designed a safer chemical? And the problem is, as Dr. Rediske has shown us, is a lot of that information comes from that environmental monitoring, that environmental toxicology, when the chemical is already out there it's already interacting with living systems. It's already being altered, maybe degraded into daughter molecules that are more toxic than the parent. And there's all this environmental fate and transport going on, and as it builds up in the environment, we start seeing the toxicity, we start seeing the issues develop, and that's kind of a signal that there's something wrong with this chemical. But by that point, it's too late. It's already out there. So as Dr. Rediske showed us, there's all that focus now on upstream of the design phase, using all that kind of mechanistic toxicology, all those predictive tools, and the power of bioinformatics and computational toxicology to try and kind of reverse that. So we can start trying to predict, our design signal can be based on foreknowledge rather than after knowledge.
Right, and that's the subject of a whole series of other talks that we can have, and that's really what's exciting about toxicology and green chemistry is there's such an opportunity to be proactive, and then once you're proactive and you design something that's good, you should be able to have a much more profitable and beneficial business out of that.
Now, so we do have another question here, which I may have already answered, but I'll just read it out, is, will more extensive testing be able to show us chemicals that could become toxic as they degrade in the environment?
Well, that's, if you put more emphasis on the design part, you may not need to have all the other testing afterward, but yes, if you look at how pesticides have been designed over the years, we still have, problems with some of them, but, the pesticides that we are making now are considerably safer than materials like DDT and that we've historically designed. So, we still have a lot of potential problems with some of the chemicals that are out there, and the science still needs to evolve to get better, but I think we are making progress. We're not using lead in paint and other things. I mean, historically things are much worse than they are now, and the problem that we have too is that as we're designing more molecules now, we're getting this issue with endocrine disruption. So we don't have the acute toxicities or some of the other the chronic toxicities before, but now we're faced with some very difficult concepts to deal with respect to hormonal systems. So we have bigger challenges. We have big challenges ahead, but as Clinton was saying, we do have tools in place to design better molecules. We can design that endocrine disruption out of some products, and I think that's much better than trying to come up with safe levels once it's out there. So that's our challenge as far as science is concerned.
Well, thank you, Rick. It's a couple of minutes before our hour is up, so I would just like to make some closing remarks, and thank you again to Dr. Rediske for providing us a great overview of a very complex subject. And I'd just like to let the audience know that this was kind of just an overview to give you kind of a taste of the challenges that we face as you think about toxicology training for green chemists. And Dr. Rediske nicely summarized some of the key areas that are going to be like the tension points. If you're interested in learning more about those topics, we will make resources available on the toxicology training website, where we can point you to other materials or other webinars that have kind of delved into some of these specific topics in more depth, like the whole issue of inverse dose response curves. Actually, in previous years, we've had webinars. The Michigan Green Chemistry Clearinghouse, in partnership with the Great Lakes Green Chemistry Network, has hosted a series of webinars, and some of our presenters in the past have dealt in some of these topics in more depth. And you can find those webinars on our website as well, and I'll make sure that they are linked from the toxicology training page.